Okay, we're very happy to have Athira here, and she'll tell us about flat holography. I'm sure that's not very familiar to all of you, but she's going to explain what it is. She's a postdoc at ICTS, and she'll tell you a little bit about herself from where she came and on before she starts her talk.
Hi everyone. So I would like to thank Sumathi for inviting me to give a talk here. So myself Athira. So I'm a postdoc at ICTS. So maybe I'll introduce a bit about myself also. My native place is Kerala, and I did my BSc from Kerala only. And I mean, when I was like at your age, I also used to think maybe it may be very difficult for me to get into some good places. But then I used to write all the entrance examinations, and then I got into Pondicherry University for my MSc. And after then, I went to Chennai Mathematical Institute to do my PhD. So there, I did PhD with Professor Alok Ladda. And in 2022, I finished my PhD. And then I joined ICTS as a postdoctoral fellow. So I kind of completed my term here last month. And now I'm going to do my second postdoc. So I'm going to join Institute of Math Science for my second postdoc. Also, I'm a mother of a 2-year-old kid. So, so actually, yeah, I mean, that is also one of the reasons Sumathi asked me to come today. And I mean, I know there is actually a misconception that it may be very difficult to do research and you have to manage the family as well. But from my experience, I mean, it's not that difficult. You can actually manage your family and a kid, your work, everything. So yeah. So now, yeah, let me talk a little bit about my work as well. So I have been, so here in ICTS, I have been working with Professor Suvrat Raju and Professor Ashok Sen. So I mainly work in the field of theoretical high energy physics. And this flat holography, this is one of the topics I have been working on. So let me give a brief introduction about flat holography. So I try to make it a bit more elementary, but please feel to stop me at any point if you have any doubts. Okay. Okay, so you must be familiar with the classical mechanics, I hope. So we know that in if you want to study the motion of some material bodies, like the some matter bodies, then you can apply the laws of Newtonian mechanics. So let's say you want to compute, maybe you want to study how some matter or some material body that when subjected to some force, how does that move? What happens to that? That you can study. And yeah, for example, using the Newton's second law, which says, which is given by F equal to ma, where F is the force, m is the mass, and a is the acceleration. So here, this acceleration, as you know, you can write it as a differential operator. I mean, you can write it as a d square x by dt square, and the force is like some differential of a potential. So then, by solving this equation and by giving the initial value, I mean, maybe if you want to, let's say you want to compute the position of a particle after some time t, then by giving the initial values like where it was at some time t0, you can solve this equation. You can compute the position at a time some x of t. Okay. So now I want to say, uh, did you have a course in quantum mechanics? I mean, how many of you had a course in quantum mechanics? Okay, fine. So, you know, I mean, yeah. So when you want to study some material bodies, actually you can use the laws of classical physics. But when you go to atomic level or some subatomic level, you cannot use the laws of classical physics to study, I mean, anything happening there. So I'll explain why that is the case. So the classical physics says light is like a wave, and let's say you take electrons, so those are like particles. But there are many experimental findings that says that suggests that the matter, like maybe the electron, that can exhibit both particle and wave-like nature. So for example, as I was saying, the electron can display both particle and wave-like nature. So that will depending upon which experiment you do. So maybe you do one experiment, you can see the electrons are behaving like a wave. You do another experiment, you can see that electrons are behaving like particles. So, but classical physics, that is inadequate in explaining this behavior. And also the light, I mean, some places you see the light is like a wave, but when you do some experiment, you see that light is like a some particle, it behaves like a particle. So then, yeah, then to explain the physics at microscopic scale, classical physics is not enough. So that is where the quantum mechanics come. So to study like both the particle and the wave aspects of matter. So when I say matter, you can always think of, so you can always decompose the matter into elementary particles like electron, quarks, which cannot be decomposed into further. So when you want to study such particles which exhibit both particle and wave nature, then you need quantum mechanics. Okay. So as we have seen in, I have explained briefly, so in classical mechanics, you solve the Newtonian equation and you solve for for x of t, the position of the particle. But because this has some wave kind of nature, I mean, you cannot really say where exactly the particle is. So there is no well-defined notion of a position or a momentum. So here we work with something called wave functions. So I mean, you can think of this as some functions which depends on the position and the time. And what you can compute is what you can find. Okay, and also it is like, as I was saying, this particle is like a wave which is spread out in space at a time t. And what you can compute is that some probability for finding the particle at a point x. And this probability is given by computing the mode square of the wave functions. So also, as I was saying, I mean, in the Newtonian mechanics, you can solve the equation, you can compute x of t after some time t. Similarly, I mean, I won't say similarly, but in a similar spirit, there is some equation in quantum mechanics called Schrodinger equation. So, you know, this is also a differential equation, some second order differential equations. And here m is the mass and h bar is a constant, which is known as Planck's constant. And this v is some potential. And yeah, so then you can solve this equation and you can find, you can find the wave function after some time t given by providing the initial values, like given some wave function at a time t0, you can actually compute the wave function after some time t. Okay. So as I was saying, the matter, it can exhibit both wave-like and particle-like nature. So then, so then one natural question one can ask is that we should view this particle nature as fundamental or some wave nature as fundamental. So then the question is like, what exactly is a consistent quantum theory for the matter? So by this I meant we want to see what is a constant theory for elementary particles. So as I was saying, this matter is composed of elementary particles, so we need some, correct theory for the elementary particles. And also I want to say one more thing. This also you must be aware of, this particles, they do interact via some forces, some like this electromagnetic forces, strong forces, nuclear forces, gravitational forces. So you not only want some theory, but you also want to explain how these particles interact and everything. Okay, so I hope the question is clear. Okay. So not only that we want some theory, but how do we know the theory is correct? So we would also like to test the theory. So so here I want to say one more thing. So when I say, so what I was saying is, so we want some theory for the elementary particles, and we also want to test the theory. And the conventional experiments which involve elementary particles, that happens in particle accelerators, where these particles move very fast. So then this would mean we need some theory for these particles which is consistent with, okay, maybe you may not be familiar with relativity, but this is some theory. This is some theory that says when the particles are moving very fast, what happens in physics. So then you want some theory for the elementary particles which are moving very fast. Okay, so there is something happens when, okay, so I want to say one more thing. So as I was explaining before, the quantum mechanics, classical mechanics was inadequate in explaining elementary particles, but quantum mechanics, so that can give the Schrodinger equation and that can explain the elementary particle behavior. But when these particles are moving with very high velocity, quantum mechanics cannot explain what quantum mechanics cannot explain the physics that happens then. So that is because when the particles are moving with very high velocity, we expect the particle number to change. So I'll explain this. Maybe you can forget about all this equation. You need only this equation actually. So basically what happens when these particles are moving with very high velocity. So, so you must be aware about the kinetic energy, which is given by half mv square. So which says that the energy is proportional to v square, but that is valid only in the low energy. That is valid only when the particles are moving with very low velocity. But when the particles are moving with very high velocity, that is close to the velocity of light, then so then energy change very drastically, which cannot be explained by using the equation half mv square. But Einstein proposed an equation to describe the energy for the particles which is moving with very high velocity. So which is this m is the mass, c is the velocity of light, and there is this gamma. So gamma has the information about the velocity of the particle. So then what you can do is that you can actually maybe let's say you have some elementary particles which are moving with very high velocity, and there is some principle in quantum mechanics. Maybe you don't know. Yeah, you don't have to go to the details, but it says that actually you can increase something so that you can actually make this energy to be equal to some 2mc square. So let's say the energy is some 2mc square. So that would mean that this equation is saying that you can always trade mass for energy. So you have some m, when you have some massive particle with mass m, then you always have some energy. So then let's say you somehow make the energy to be some 2mc square. So then I can say that okay, there are two particles with energy some mc square. So it's like particles are creating out of nowhere. So that is what I said when I meant when particles are moving with very high velocity, we accept the particle number to change. I can also give you one example for that. So this is a famous example. This is known as beta decay. So here it is a neutron. There is a positron, there is an electron and an antineutrino. So you see this decay is like there is this one particle here that is decaying into three particles. So this is an example where the number of particles is it's changing. So maybe you can think of in this way. You have some two elementary particles that those are moving with very high energy, and those are you can also study some scattering of these particles. So those if there is okay, so if there is no force, then they just move freely. But if there is something, then they will interact and they just scatter. And so I want to say so we're saying when at high velocity, so this particle, in a scattering, for example, the particle number can change. But the quantum mechanics, so I have shown you the Schrodinger equation also. You can just go back and just show you once more. Yeah. So this equation, which you solve for the wave function after some time t, but when you have a process where the particle number changes, then this equation cannot be used. You can use this to solve for a single particle, and if you have some multi-particle also, you can actually use this equation to solve for that theory. But when you have a process where the particle number changes then you cannot really use this Schrodinger equation. So basically, quantum mechanics won't work if you have particles which are moving with very high velocity, like, yeah. Yeah, sure. So, yeah, one example, as I was saying, you see, this is some decay process. We have a neutron here that is going into 3 particles. So it's something like maybe, okay. Yeah, so as I was saying, these particles actually, so if there is no interaction, there is nothing, no force, then they just move freely. But if there is some force or something, then they can interact. So when you, maybe you can actually imagine some big bodies interacting and then going, but then you don't see maybe if they scatter with very high velocity, then you can see the number of particles change, right? So in the similar way, with the elementary particles, let's say they are in some proton and some neutron, or maybe proton and electron, they are coming and interacting, and then they are going to some other particles. So these processes also, okay, so as I was saying, you have, so so ideally one would expect you can, so this is some scattering problem. So you would like to solve this problem. So you have given some like this wave function for the electron, and you have some wave function for the proton, and you want to see what is this after the scattering. But I'm saying you can actually solve, this is an equation which you can solve. Let's say you have 2 particles. So then I have some psi1 and psi2. You can substitute here and you can solve for that equation. But when you have a process where the particle number change, then this equation cannot account for that. So yeah. Yeah, but you don't, okay, fine. So let's say you have some process where 2 particles go into 3 particles, but you don't have something for the, you don't have something for the 3rd particle here, right? So it's some, yeah, because you see how this is engineered. Okay, so then, yeah, so I was saying, so then when you have elementary particle which are moving with very high velocity, then you need some theory which can account for, that formalism. So this new formalism is known as quantum field theory. Not sure whether you have heard of this, because you will be studying, you must have had a course in classical mechanics, and then you will be studying quantum mechanics. After quantum mechanics, you will be studying quantum field theory. So, and it is also important in the sense, so eventually we want to study how the universe is formed and everything. So you see, after Big Bang, these particles were moving very fast, and all the elementary particles were created, and they were moving really very fast, like fast in the sense with a high velocity, close to the velocity of the light. So then, if we have such a formalism, then that would be the closest formalism where one can really study about our universe. So that is the importance of this theory. Yeah, I'll explain a little bit about this theory. It is, explaining will be beyond the scope of this talk, but I'll explain a little bit. Okay, so as I was saying, quantum field theory is a theory which is needed when we address together quantum mechanics and, I would say, the quantum mechanics of elementary particles when they are moving very fast. Yeah, maybe I'll just say this name also, like when we address together special relativity and quantum mechanics. So special relativity is a theory when everything is, particles are moving at very high velocity, close to the velocity of light, and you have this quantum mechanics, which is the theory for the elementary particles. So here, what you have is that you have something called some function. You can think of this as some function, which is like a field. It's like, it's a function of space and time. So it is something which is defined everywhere. And maybe you've heard of this electromagnetic waves and electromagnetic field. So you can think something similar to that. And the idea is that this field, this can create particles, it can destroy particles. So then, when you then when you want to, yeah, I mean, maybe explain explain some scattering of this form, then you say that, okay, let's say I have some field for this neutron, and I also have field for each of these particles, so that now I can also explain why there is a creation of new particles happening, because I have a field which is creating these new particles. That is kind of the idea. Yeah. Yeah. So this field, it can create and it can destroy the particles. And there are different, maybe you can forget about all these words, but there are, I just want to say there are different fields. So you need, maybe for the electrons and quarks, you have some field, some which is called some spinor field. And then for the light, you have something called vector field. And for the bosons also, you have something called, I mean, scalar field. And this, yeah, I mean, this word, yeah. So these, each of these fields are different. Obviously, each of these particles are different. So then these fields will also be different. But I mean, not only that, because I'm saying because these particles are like moving very fast, there is some laws, some transformation laws and everything. So this field also has to obey the physics um at those energies. So I want to say these particles, they also have to obey the physics of relativity. So then they transforms in a nice way. Yeah, yeah. Field. Yeah, yeah. I mean, okay. So fine. It is. We can think of it as some function of. It has something. It's a function of the space time. So it's like it has a value at every point in the space. So it is, this like this electromagnetic wave, which is also something which has value at every point in the space. So this also sort of like that. It's also some field, I mean, some function which is defined at each point in x. So it is different from the wave function. Okay, I mean, it's very different concept, because I told you in quantum mechanics you need some wave function because the particles have some wave nature. Then you have some wave function, but that is for one particle. So you have one particle, you have some wave function, which is some spread out in space. But this is like, it can create any particles. It's very different from that. So you don't have particle now. You only have field. You only have something as fundamental, some field, and it creates all the particles. So now you don't have electrons, you only have field. So you don't have to give, I mean, it's it's not a function of anything, but you have some field and it creates all the particles. It creates everything. Yeah. So it can also actually be right. Okay. Maybe I won't go into detail, but so there are some operators also, some operators called some creation annihilation operators. So this field you always write in terms of those operators. And those operators, they create particles and they destroy particles. It's kind of, idea is kind of that. So, and when you consider some scattering, like some neutron and go into something, then you have some field which there is some, I mean, if the neutron were very free, then it won't, this process won't happen. But there is some force, some interaction. So what you do is you write the interaction also, everything in terms of this field. And then you can explain this theory. So you have some field for each particle, and you also have to see, you have to give how, I mean, why this is happening, what is the potential. So you need the potential as well. So you write the potential also in terms of the field. Then you can solve for this problem. So by solving, I meant, okay, so this is kind of a scattering. So, I mean, you can actually find some amplitude, some cross section. In the classical scattering also, you can actually find some cross section and everything. So similarly, here also, you should be able to find some cross section, some scattering cross section, kind of a concept using this field concept. So that is the idea. So basically, you need to provide all the interaction, or I mean, how it interacts. So that all you have to provide by, I mean, yeah, by giving this in terms of these fields. So that is roughly the idea. Is it okay? So, and okay, I also want to, maybe you can just forget about all these words, but there is actually very well defined theory for this field for uh, this quarks and everything, that is called some QCD, and there is some theory for this photons, that is what's called, that is called some quantum electrodynamics, and these are very well defined theories. Now, okay, so I also want to say one more thing. So as I was saying, these particles actually they interact also. So then there are four fundamental forces in nature, like electromagnetic, strong, weak, and gravitational forces. So these particles, they interact via this forces. So then when you say you have some theory, some quantum theory, which explain the scattering of these particles, then you should also be able to explain all these type of interactions. But there is something called, but there is this theory we know up to now, it cannot explain gravitational forces. So basically, when you try to write some theory for the gravitational forces, you see some infinities, which you cannot, which cannot be regulated. I mean, there are some infinities, which is not a good theory for you. Because when you do experiments, you don't get any infinities, you get only finite answers. But this theory, I mean, when you write the theory for such force, then, yeah, I mean, you do get some infinities. So then, yeah, so the quantum field theory works very well for all the other forces except gravitational forces. And there are, there are many physicists working on this actually. And one theory, one closest theory to explain the gravitational force is known as string theory. I won't explain anything, but I mean, this is the name of the theory. And also, okay, so maybe you can forget about this also. So I just want to say this, the field theory, which is a theory for relativistic elementary particles, means the elementary particles which are moving with very high velocity, but that cannot explain the gravity. I mean, if there are these particles which are interacting by a gravitational force, this cannot be explained by this theory. Okay, so I work in mostly in this area of quantum field theory, and maybe now I'll tell a little bit more about what I have been working on. Okay, so I work in some concept called holography. So I'll explain a little bit. I won't explain much. So holography is the idea that a two-dimensional image, it can store all the information about a three-dimensional object. So maybe you can think of some bowl, and so you have some like you have some think of some bowl actually. I don't know, some 3D object, and you have some. Then this idea would mean that whatever happens here, and this boundary, I mean, this I call the boundary. So this has the information about whatever happens inside. So this is roughly the idea, but when it applies to some theory, some field theory, when you have all the elementary particles which are scattering off, then this would turn into something called, you have something like you have some so this you can actually think of some space, like some three-dimensional some space. This also some other space, and you have some particle scattering here, and you have some theory for that, and you also have something happening here, something happening on this edges, and you have some theory for that. And then so in quantum field theory, okay, so this idea is that these two theories, the theory you would use to explain some similar to this process here on this edge, that is same as the theory you would use to explain some scattering happening in the bulk, I mean, happening in this region. So the main use of this theory is that, I'll tell you that again. So in quantum field theory, what we see is that the theory in the bulk, it has some gravitational forces. I mean, you actually here there are some of the particles which interact via the gravitational forces, but here these particles they are not interacting via gravitational forces. So it's something like so as I was saying before also, you don't have a quantum field theory for the to explain the gravitational forces, but then this holography would say that okay, you can I mean okay, you can explain something happening here which involves some gravitational forces by using some theory happening here which doesn't involve any gravitational forces. So then, I mean, which is very strong concept. It is because we still don't have a complete understanding of this quantum theory for gravity. But then you can always use this whatever happens here without any gravitational forces to study whatever happens inside. But this is also not very complete. But we actually see these are equal in some cases, some scenarios. So this is a very powerful tool in quantum field theory to study this kind of scattering involving gravitational forces. Okay, and there is also another thing. So this concept is also not known for it's not in general. So by that, what I meant is that this is only studied in something like this, some curved curved space. Curved, I mean it's not flat, it's just something like this. It's only studied in such scenarios. So but to so as I was saying, by understanding the symbol theory in the boundary, you can actually learn more about this. Maybe forget about quantum gravity, more about the gravitational forces, more about when these elementary particles they interact via gravity at high energies. Okay, so now so this as I was saying, this doesn't work for everywhere. It only works for some like something like this. This is like a curve, some space. Doesn't work for everywhere. But if you want to understand about our universe, and if you want to understand about the theories, this how particles scatter in our universe, then you need to understand something similar in flat space. Like you can actually think of our universe as something flat. So you need to understand something like such theory in a flat space. So this is what I have been working for the past years. It's very hard problem. I'll tell you why it is a hard problem, because you see, this works. This you have some boundary kind of thing here, but in flat space time it just goes to infinity. So you don't have a boundary. It's like everything just goes to infinity. So then where will you study any theory? Okay, let's say you have something happening inside with the gravitational forces, and you would like to understand that by using some simple theory on the edges, but you don't have a edge now. So that is why this is very hard. And this is also, that's why it's also not well studied. I mean, there has been many works, but this problem is very hard. Yeah, so that's what I want to say. So this our universe is, it's like on large scale you can think of this as flat, and to study some gravitational forces you can forget about everything, but we need something like some holography for some flat space. So that is the idea of concept of flat holography. Okay, so I actually work on this maybe. Yeah, as I was saying, and one of the challenges is that in flat, forget about space time, maybe in such a scenario you don't really have a boundary because everything just goes to infinity. And then but actually there is actually a tool. So as I was saying, everything just goes to infinity, but you can actually write down some equations, and you can actually whatever is at infinity, you can actually write some diagram where it looks like everything is at finite distance. That can be done, and that is known as this idea called Penrose diagram. And you can actually study this concept of this holography using this diagrams, which is known as Penrose diagram. Okay, maybe I have only one more slide. I'll just end my talk by just saying that slide. Okay, forget about everything. Maybe it is this diagram I'm seeing, that is something like this. You see. So as I was saying, so you don't have a boundary, but you can. This is the space you are working. This is the bulk, like this. But you can attach some boundary, and it won't be simple. It won't be one boundary. You will have multiple boundary. Like here you only have one edge, but if you try to do it in real, if you want to do it in the real universe, then this is very complicated. You can have multiple boundaries, and these all these are very different. And yeah, so many work have been done over years to understand the holography at this boundary, and we also did some works in like these two of these boundaries. Yeah, so I'll end my talk here. Maybe you can ask questions, because it was like very, I didn't really go into any much details. It was all like very brief introduction. Maybe you can, yeah, it's time for questions. You can ask me more questions now. Yeah, yeah. Okay, yeah. Yeah. Yeah, sure. So you see, okay, the non-concept of holography in field theory, that doesn't work for, okay. So, there are different spaces. So not, you can consider this sphere, which is a curved space. And there is this cylinder, that's also different space. And there is this flat, like something like, which is very flat. But the non-holography concept, that applies only to curved surface. That doesn't, yeah, we don't know actually. We only have such concept for a curved surface. We don't have anything yet. But you see, at the end, actually, we really want to understand about our universe. But then, which is not, and this curve, which is not curved, that is actually okay. There are actually different spaces, like some anti-de Sitter, de Sitter, flat, everything. And universe is like a space with positive cosmological content. That is a very different space. It is actually de Sitter space time. But then at the end, we want to understand this concept in a de Sitter space time. You can just think about some space. It's like some curved space time, but it has a negative curve. It's not exactly. In the sense, there are this parabolic spaces and everything. This parabola. You can actually think about some three-dimensional parabola. So you can have a parabola with post like this. You can have parabola something like this. You can have something like this. Just think about in higher dimensions. You really have to think in 4 dimensions, not even 3D. Maybe for now you can think about in 3 dimensions. And ADS spacetime is some spacetime which falls into one category, and DS is another spacetime which falls into another category. And our universe, that is like a de Sitter spacetime. But we don't have, but it's actually, but we don't know this, when I was saying about this quantum field theory and everything, which is a theory for the elementary particles which are moving very fast, we actually don't know how to study scattering in de Sitter spacetime. We don't have the theory yet. But in another spacetime, which is also called ADS, there you have, the theory, you actually have so much information there. So then by using that, we would like to study about our universe. So then we would really be studying about the de Sitter space. But that is very hard. Then the closest approximation to our universe is flat. So better to study in flat about this theory. So, but this also not, this also like not developed, maybe in, I don't know actually, maybe it takes years probably. Yeah. Yeah. it's not like, okay, that is the idea. Fine. Yeah.
But then multiple bulk or multiple 3D spaces or regions can have this similar type of boundary, right?
True, true. Yeah, true.
So then is there a way of like representing the boundary space that's unique for each region?
Okay, 1 second. I mean, okay. So if you think about simple examples, that may be true. That is the case. But uh, when you, yeah, when you think about, I mean, not about some, not about some 3-dimensional. When you think about higher dimensions, and this, the spaces like this, like what I'm talking about, what we really do in field theory, like this ADS space, DS space, flat space, they only have one boundary, and you can actually study the theory there.
Multiple things are there. I think you're talking about the usual hologram that you've seen, right?
Oh, that.
Right? So comparison would be to a normal hologram. How is it that on a flat space you're going to see a 3D? Right? How would you compare?
Yeah, this.
Meaning the information that you have in 2D seems to be less than the information that you have in 3D.
Oh, okay.
Many 3Ds which will have the same.
Yeah, that is true. That is true. Yeah, that is true.
So how is it that you're getting all that extra information? It's like in a hologram.
Yeah.
You can do it.
Yeah, that is true. That is true.
You've seen a hologram. Not in real life. Yeah. Oh, you've seen pictures of it. I've seen it, but I've also seen it abroad. So the question is, how do you get all that extra?
Yeah. Okay. So actually, yeah. One thing about this, the non-holography, is that we really still don't have the full information. We only know, when I say theories are equivalent, we only know, that's also not completely known. Okay, we can actually compute something here and something there, and there are few things we can actually show that those are same, but not everything. I mean, not all calculation you do there, we don't know actually. I mean, we don't know why this is happening, but we know it is happening. Only when we know why this is happening, then I think I can actually understand, I mean, answer your question as well. Yeah.
You said it's flat, right? On the hologram. Is that just a mathematical convenience that we take, or because I mean?
Yeah, actually, that is true. That is true, because, but I won't exactly. It is mathematically convenient. I agree that, but it is still very hard. So when I'm saying about this, whatever we know, we have some theory for the curved space-time, but that is also curved. That is not flat. But still we know everything. I mean, we have some not everything, but some idea, more idea there. But even though it is flat, that is not actually, yeah, as I was saying, so the flat space, that just goes to infinity. We don't have a boundary also. So I mean, it just goes to infinity. So that makes it very hard. So we have to find some mathematical tool, something like this, some figure, something like this. So these boundaries, actually, these are really at infinity. But you can use, by using some equations and some transformation, I say, you do some coordinate transformation and everything, you can actually bring those boundaries to some finite distance, so that we can do some calculations. So yeah, no, these are like different spaces. So that is another space, and this is another space. So I mean, and we know this concept of holography very well, yeah, to some extent in that curved space. But we want to understand something about our universe, then it is like, yeah, then we would like to see, actually understand this. Actually, yeah, basically we want to understand all these forces, all these elementary particles, and we want to understand how they interact via all these four fundamental forces. We want to understand everything. But we have, I mean, when it comes to gravitational forces, we don't have the theory. So that is why this concept of holography and everything is introduced. I mean, not introduced, it is useful. Yeah. This one. Oh. Okay, okay, okay. So, um, fine. Okay, so the idea is that, okay, so you see, you have all these massive particles, massless particles and everything. So that also, I mean, when I say elementary particles, you have like the light, which is the quanta of photons, and you have electrons. So basically you need to study the scattering of all these particles. And this different boundaries, those would say, okay, those are useful in the sense, you see the massive, okay. Fine. So you can also solve. So these particles, they do follow some equations of motion. They are not random. So they do follow some equations of motion. So they according to that equation of motion, they they scatter off. So then these boundaries says, so for example, this massive particles, they live, I would say they live on these two boundaries. So that is how they they scatter in the flat space. And the massless particles, they do live on this boundary, in the sense this is the way the light, it actually goes like this in a scattering process. And the massive particle, like the electron, it goes like this. So this boundary says that, all these particles, they behave very differently. So it kind of say about the trajectory of these particles. Also, I want to say one more point. So I was saying this is like, so you have this, for the flat space, you have this boundaries at infinity. And this is only one construction where you could actually consider these boundaries as boundaries in the finite space. But there are other constructions as well. This is only one tool, one mathematical tool. So I just want to make this point.